Hello and welcome to the fourth and final video of the FP2 chapter second order differential equations. Quite a long starter on the screen. If you've got time, pause the video now, give this a go for yourself. The displacement, x, of a mass on a spring oscillating with time t can be modelled using the second order differential equation, this. Solve to find the particular solution when c equals 1 with the boundary conditions, these. Okay, first thing we are going to need to do here is to put this into a format that we can recognize. So I'm going to put all of this onto the left, and because we know we're solving when c equals 1 specifically, I will put that in now. C is 1, so this becomes dx by dt plus x is equal to 0. So x is in the position that y is normally in, and t is in the position x is normally in. So we just go ahead and find the complementary function, and that is our solution. In this case, we get a complex conjugate pair, minus a half, plus or minus root 3 over 2 I. That tells us that x is equal to e to the minus half t, a cosine root 3 over 2 t, plus b sine root 3 over 2 t. And because this is equal 0, we don't need a particular integral. This is the general solution. Now we need to find the particular solution when these boundary conditions here hold true. So x equals 1 when t equals 0, we can put that in this equation straight away. And that gives us 1 equals 1 brackets a plus 0. So a equals 1. Now our second boundary is the first derivative of x equals 0 when t equals 0, so I need to find the derivative of this. That's what makes this slightly longer. I have to use the product rule, and I can use that treating the bracket as one element and the exponential as another. So if I differentiate the exponential first, and then leave the bracket alone, then leave the exponential alone and differentiate the bracket, and then we have plus root 3 over 2 b cosine root 3 over 2t, and that's looking quite horrible, but we know that this equals 0 when t equals 0, and if t equals 0, and we also know a equals 1, this becomes minus a half 1 plus 0 plus 1 times 0 plus root 3 over 2 b. Rearranging that gives us a half equals root 3 over 2 b, so b must equal root 3 over 3. So our particular solution is x equals e to the minus a half t, a is 1, so that's cosine root 3 over 2t, and b is root 3 over 3, sine root 3 over 2t. Now that looks quite horrible, but there's something to say about this. If we've got a mix of sine and cosine, then that is some wave function. But then we have this multiplier in front, and as t gets bigger, this gets smaller. So as we go along, the wave amplitude gets smaller and smaller. If I clear this off for a second, I can show you what the graph looks like. Here we go. And this is important to note because this is known as a damped oscillator. It's oscillating, going backwards and forwards, but as it does so, the amplitude gets smaller and smaller and smaller. That's the damped part. And that's quite important in physics and engineering. In this video, we're going to take these ideas and we're going to add in the idea of substitution, which we had in the previous chapter for first order differential equations. So we're going to reduce SODE to something that we know how to solve in this form or this form. So the notes are quite simple. Just as with first order differential equations, more complicated second order differential equations can sometimes be reduced to something we can solve using an appropriate substitution. And almost always you'll be given the substitution. Quite often you will also be told what to expect from that substitution. Something like this. Show that the transformation this, so they're giving the substitution, transforms this equation into this equation. So they're also telling you what to expect, what to aim at. You can see that we're substituting out y and we're bringing in v. And no doubt you can see that this is going to be much easier to solve than this would be. So our method, just as with first order differential equations, we need to find expressions for the first derivative and the second derivative of y with respect to x in terms of v and x. Then we substitute for that, and also the y given the original transformation. Simplify it to get the required form. Okay, let's do that first. If we've got y equals xv, then dy by dx, using our product rule, differentiating with respect to x, is a v plus x dv by dx. For the second derivative, we just take that and go again. Differentiating everything with respect to x again gives dv by dx. And the product rule again, plus dv by dx plus x d2v by dx squared, like that. Then of course, if we wanted, we could simplify that by adding those two together. So we have our expressions for y from the question, dy by dx and d2y by dx squared. We can substitute those in here, here, and here, and hopefully that will simplify to give this expression here. Change into, let's go blue, x squared times 2 dv by dx plus x d2v by dx squared minus 2x lots of the first derivative of y, v plus x dv by dx, plus 2 plus 9x squared times y, which is xv. And all of that has to equal x to the power 5. Expanding all of those out, 2x squared dv by dx, x cubed minus 2xv plus 2xv. Okay. Now, fortunately, a few of these things cancel out. They're gone, and these are gone, and we get left with x cubed d2v by dx squared plus 9x cubed v equals x to the power 5, and then dividing everything by x cubed gives us our required result. Like so. Now that we've got that, we are ready to do the next step, which is to solve the differential equation to find v as a function of x. This 2 here refers to the second differential equation, and this is the first one. So that's just an easy way to tell them apart. So we're solving this one here. And we do that with all of the methods that we've used so far to solve second order differential equations. So let's go ahead and do that. We need the complementary function. In this case, we've got m squared plus 9 is equal to 0. M is plus or minus 3i, which gives v equals e to the 0x, that's a 1, a cosine 3x plus b sine 3x. Then the particular integral, in this case it's a quadratic, so I will try v equals lambda x squared plus mu x plus nu. dv by dx is equal to 2 lambda x plus mu. Second derivative is equal to 2 lambda. Substituting those into our equation gives me just a 2 lambda plus 9 lots of lambda x squared plus mu x plus nu. That has to equal x squared. So we've got 2 lambda plus 9 lambda x squared plus 9 mu x plus 9 nu equals x squared. So 9 lambda equals 1, lambda equals 1 over 9. 9 mu must equal 0 for the x's, so mu equals 0, and 2 lambda plus 9 nu has to equal 0, so that's 2 over 9 plus 9 nu. Nu must equal minus 2 over 81, which gives us a final particular integral of v equals 1 over 9x squared minus 2 over 81. And a final general solution, v equals a cos 3x plus b sine 3x plus 1 over 9x squared minus 2 over 81, where this is the complementary function plus the particular integral. Next, we need to state the general solution of the differential equation 1. So we've solved this one, and we need to state the solution to this one. To do that, all we're being asked to do is to change back to the original variable. To do that, we use the transformation given in the question. So here we've got this solution. We know that y equals xv, so we just change that around. V is equal to y over x. So changing this solution here, just replace the v with a y over x. That means if I want y, I multiply every term by x, so we get ax sine 3x plus bx cosine 3x plus x cubed over 9 minus 2x over 81. And this is the final general solution of the differential equation 1. So all the methods there were the same as with first order differential equations, but it might just take you a bit more time. And often that will be because of this bit, needing to find the second order derivative of your transformation to be able to substitute that into the equation. What's different with this example is that we don't have a y in the transformation. We've got x connecting with u, and we're going to substitute the x into a u rather than substituting out the y into something else. Don't let that worry you. You can still get a y into this by differentiating all of this with respect to y. So if we start with that, we've got x equals e to the u. That's useful. But to get a dy by dx out of this, we first need dx by dy. Differentiate everything with respect to y. On the right hand side, we differentiate with respect to u first, e to the u, and then times by du by dy. And you can see that we've got the two bits we need here. We just need to invert this. Change everything onto the other side, or do 1 divided by everything depending on how you think of it. That will give us dy by dx. A 1 over e to the u on this side, so I'll bring that onto this side. Dy by du. Now to get this statement here, all we need to do is recognize that e to the u is equal to x. So I can change this e to the u into an x. And that gives us our first statement in part A. To get the second derivative, it's a bit more work, and you can either start with this statement and differentiate everything with respect to x to make sure you get the second derivative of y with respect to x here, and then deal with all the other stuff that you need to make it look like this. Or you can go back to this statement and differentiate everything with respect to u to make sure you get the second derivative of y with respect to u, and then deal with everything else you get on this side to get this and this. Whichever way you do it, you'll get the correct answer, so long as you don't make any mistakes. But sometimes one way will be quicker than another. Unfortunately, you won't necessarily know which way is quicker until you've tried it. So I'm going to go with this one, and I'm going to differentiate everything with respect to x to make sure that I get this term here. Straight away, you can see that I'm going to have to use the product rule on the left. So if I differentiate x and leave dy by dx, and then leave the x alone and differentiate dy by dx, I get the second derivative that I knew I would get. On the right, I have the second derivative with respect to u, And then to do that while differentiating with respect to x, I need to times by du by dx. Now, to make this look like this, have a think. This is okay, I want this term. This is okay, I want this term. I don't want a dy by dx in this expression, but I know what dy by dx is equal to. I have an expression here. So I can substitute this with this expression to get 1 over x dy by du, and I do want dy by du's. I also don't want du by dx, and I don't yet have an expression for that here, but I do have an equation connecting x and u. So what I can do here is just differentiate this. Dx by du is equal to e to the u, and that gives me du by dx is equal to 1 over e to the u. And at various points through this process, I need to remember that x equals e to the u. So for example here, I can change this into a 1 over x. So du by dx is the same as 1 over x. So I can substitute that in there. Here, dy by dx is the same as 1 over x dy by du. So I have 1 over x dy by du plus x, second order derivative here that I did not want to change, equals the second order derivative here that I did not want to change, times by du by dx, which I now know is equal to 1 over x. Multiply everything by x to get rid of those fractions, and I'm almost there. This gives me dy by du plus x squared is equal to this. Simple bit of rearranging now gets me the result I need. So in purple, we've got the answer to part A, and in red here, the answer to part B. The reason we're doing this is so that we can now solve this equation here. I'll get rid of this in a second. You can see why they're leading us through this, because this part here is right here. So I can substitute this directly for this. And this part here, x dy by dx, is here. So I can substitute this, not forgetting the 3, into this. This is the sort of question in an exam where even if you stumble and can't quite do these bits, because they've told you what to expect here, you can still do this bit even if you haven't completed these bits. So substituting these in, we're going to have d2y by du squared minus dy by du in place of this first term here, plus 3 lots of x dy by dx, which we know is dy by du from part A, minus 3y is equal to 0, and the two middle terms can add together. So we've got a second derivative plus 2 first derivatives minus 3 of the function. And this is our second order differential equation that we can solve by using the complementary function. M squared plus 2m minus 3 equals 0, m plus 3, m minus 1. So our solutions here, m equals minus 3 and m equals 1. So our final solution for the equation in terms of u is y equals a e to the minus 3u plus b e to the u. But remember, we don't want u in our final solution because this equation doesn't have any u's. We want x's. To change this back into x's then, we go right back to the original transformation, and we note that if x is equal to e to the u, then u must equal natural log of x. And we can substitute that back in here. That gives us y is equal to a e to the minus 3 natural log x plus b e natural log x. And you can see here that the e and the natural log will cancel. If you manipulate the minus 3 into a power, you can do the same here to give us a final statement, a x to the minus 3 plus b x. So I hope you can see that we've got a very similar method each time. We're trying to find something to substitute out the derivatives, the first derivative and the second derivative. If it's a little bit more complicated than that, they will probably lead you through it in the question. and then you'll get an answer with that dummy variable, which needs to be substituted out at the very end for whichever variable was in your original equation. So I have one final example, and it's this. But before I go through this, I want to make it clear that this is one of the questions in exercise 6D. And it's not a very long exercise. There are only 5 questions. So if you want to do exercise 6D, stop the video now and do those questions in exercise 6D and also the chapter 6 review exercise. And then if you would like to, come back and check your work on this question. If for whatever reason you're not going to do those questions, or you don't mind not doing all of them, then stick around and we're going to go through this one. Again, here we don't have a y in our transformation, but we do need a y in order to substitute these derivatives out. So I'm going to differentiate this with respect to y, and that will give us dz by dy is equal to cosine x dx by dy. Then I'm going to flip it all upside down. I'll bring the cosine on the other side so that I don't turn that into a secant. We get cos x dy by dz is equal to dy by dx. Now for the second derivative, it's the same decision as before. You can choose either z or x, and whichever one you differentiate with will give you the second order derivative that you need. So if I differentiate all of this with respect to x, I get minus sine x dy by dz, applying the product rule, plus cosine x d2y by dz squared times dz by dx is equal to second order derivative of y with respect to x. Also, as before, I've got a derivative in here that I don't yet know and do not want, but I can find that by considering the original equation. If z is equal to sine x, then dz by dx is equal to cosine x. So I can substitute that in here to get minus sine x dy by dz plus cos squared x d2y by dz squared is equal to d2y by dx squared. Now I have an expression for dy by dx and an expression for the second order derivative. Substitute those back into here and here, which gives us quite a long expression. Cosine x times minus sine x dy by dz plus cosine cubed x d2y by dz squared plus sine x times cosine x dy by dz minus 2 times y cosine cubed x is equal to 2 cosine power 5x, which is not as bad as it looks because this term and this term simply cancel out, and then I've got cosine cubed, cosine power 5, so I'll divide everything by cosine cubed, which simplifies quite nicely down to this. But this is not quite finished because I've got y and z, because I've substituted out x for z. I can't have x here, I need a z. To connect that with z, I need to remember a sine-cosine connection, and I can change this into 1 minus sine squared x, and sine x is z. So this becomes second order differential equation this, which might not look very nice, but it certainly looks nicer than this thing up here. So our next step, now that we've done the substitution to get a second order differential equation that we can solve, is to go ahead and solve it. This will give us y in terms of z. Here it is, I've got a bit more space here. Complementary function. Using the left hand side, we've got m squared minus 2 equals 0. That gives us m is plus or minus the square root of 2, which means y is equal to a e root 2z plus b e minus root 2z as our complementary function. For the particular integral, I'm going to try a quadratic equation. first derivative, second derivative, substituting them in, I need a second derivative, so that's 2 lambda minus 2 lots of the particular integral itself, and that has to equal 2 minus 2z squared. Equating the z squareds, we've got minus 2 lambda equals minus 2, so lambda equals 1. Equating the z's tells us that mu must equal 0, because there are no z's on the right hand side. And then we've got 2 lambda minus 2 nu equals 2 for the constants, and we know lambda is 1, so that's 2 minus 2 nu equals 2, which means nu must also equal 0. So our particular integral is actually quite nice, it's just z squared. That means our general solution, complementary function plus particular integral, is equal to a e to the root 2z plus b e to the minus root 2z plus z squared. But of course we can't leave it like that, because we can't have a solution including z's for an equation that is involving x's. Substituting back, z is equal to sine x, just throw that back in. So we've got y is equal to a e root 2 sine x plus b e minus root 2 sine x plus sine squared x. And although it doesn't look very nice and can't really simplify, that is our general solution to this differential equation here. So if you haven't already done so, you can now try exercise 6D, the other 4 questions, and all of the chapter 6 review exercise. If you need more practice on this, the challenge questions from this point to the end of the chapter all focus on substitution as well. Maybe I'll see you in chapter 7.